Hello, everyone. Today, we are presenting AidSync, a simulation study on capacity coordination for humanitarian food logistics in Nigeria. Our project focuses on how food aid enters the country through Lekki Deep Seaport, moves through port handling and customs clearance, and is then transported to downstream agencies. We use ProModel to simulate this logistics chain and identify which resources most strongly affect system performance. Our presentation is organized into 5 main parts. First, we will introduce the motivation and background of the humanitarian logistics problem. Second, explain the simulation model and major assumptions. Third, describe the research design and the 2 main problems we want to solve. Then, we will present the key simulation results and conclusions. Finally, discuss model validation and verification. Nigeria is facing a serious humanitarian food security challenge. More than 33 million people are facing crisis or emergency-level hunger, and food assistance from the World Food Program is critical for many communities. In this context, logistics is not just an operational issue. It directly affects whether food aid can reach vulnerable populations on time. Therefore, improving the efficiency of food aid transportation has clear humanitarian value. The logistics challenge is caused by several connected factors. Nigeria has widespread poverty, regional conflicts, and underdeveloped inland transportation networks. Many high-need areas are located far from the southern ports where international aid usually arrives. This means that food aid must pass through a long chain of port handling, customs clearance, inland transportation, warehouse processing, and final delivery before reaching agencies. In our model, Lekki Deep Seaport is selected as the main entry point. This is because Lekki Port is a newer and more advanced port with stronger operational capabilities. However, even if the port itself has high capacity, delays can still occur if inland transportation and warehouse processing cannot keep up. This is why our project focuses on coordination across the whole system, rather than only improving the port. This slide presents the structure of our simulation model. The model is divided into 2 connected parts: inside port operations and outside port operations. Inside the port, the process starts with ship arrival, followed by berth unloading, yard transfer, customs clearance, and movement into the pre-staging buffer. These steps mainly use portside resources such as the STS crane and internal terminal vehicles. After containers leave the port, the outside port process begins. Trucks dispatch containers to the warehouse, where they are unloaded, sorted, repacked, routed, and finally delivered to downstream agencies. To keep the model focused, we make several assumptions. Food aid is treated as non-perishable. Shipments arrive at Lekki Deep Seaport every 60 days. Storage capacity is sufficient, and workers follow mandatory rest schedules. The full model is built in ProModel, and SimRunner is used to search for the optimal number of resources. The model inputs include 272 containers per ship, 95% normal customs clearance with 5% extra supervision, and daily dispatch levels of 20, 25, or 30 containers. Our research design focuses on 2 problems. The first problem is bottleneck identification and resource allocation. We want to find the best combination of internal transportation vehicles, trucks, and warehouse equipment to minimize time and cost. The second problem is system performance under demand change. We compare the optimized results under 0.5 times, 1 times, and 2 times demand levels to see whether the system responds proportionally as demand increases. This slide summarizes our main simulation results. First, under the nominal 1x demand level, the optimal resource set includes 1 STS crane, 12 ITVs, 6 trucks, 1 container forklift, and 44 box forklifts. With this configuration, the total cost is $48,818.78. The truck-related time is 6.06 days. The yard time is 7.94 days. And the final completion times for the 3 downstream agencies are around 19 to 21 days. The key point here is that the model does not simply choose more portfront resources. 1 STS crane is enough under normal demand, while ITVs, trucks, and warehouse forklifts are more important for keeping the whole system synchronized. On the right side, the demand scaling chart shows how the system changes from 0.5x to 2x demand. Cost increases from $27,769.78 to $48,818.78, and then jumps to $128,000 and $81.35. Truck-related time also rises from 5.58 days to 6.06 days, and then sharply increases to 15.60 days under 2x demand. This shows that the system response is nonlinear. When demand doubles, the pressure is not only on the port, but also on trucks and downstream coordination. Therefore, the main conclusion is that humanitarian logistics improvement should focus on system-wide capacity coordination, especially truck availability and warehouse-side handling. The sensitivity analysis identifies truck shortage as the most serious system-level bottleneck. When the truck level is reduced to the truck 2 scenario, downstream completion times increase by about 52 to 56%, and truck-related time increases by 169.03%. This means trucks are not only transportation resources, they also coordinate the movement between port release, warehouse inflow, and final delivery. For validation, we first conduct conceptual validation. The model structure and input parameters are reviewed against public datasets and industry reports. The two-stage workflow in the model matches the real humanitarian logistics process. Food aid enters through the port, passes through customs and pre-staging, moves by truck, and is then processed in the warehouse. This gives the model strong face validity. We also conduct operational validation using 100 independent replications. The key metric is the average container dwell time. The 95% T confidence interval is from 9.80 to 10.61 days. Since the real-world benchmark value of 10 days falls inside this interval, the model is statistically consistent with observed port performance. This supports the reliability of the model for strategic analysis. For verification, we check whether the ProModel implementation is correct. First, we review the model logic and trace the animation to ensure entities move through the intended routes. Second, we examine demand scenario calibration. Event counts increase proportionally across 0.5 times, 1 times, and 2 times demand levels. Third, we vary key resources such as forklifts, trucks, and ITVs. The model responds in logical ways, which confirms that the implementation is working correctly. To conclude, our simulation shows that improving humanitarian food logistics is not only about expanding port capacity. The key is to coordinate port release, truck availability, and warehouse handling as one connected system. Truck shortage causes the largest system-wide deterioration, while warehouse resources also play an important role in reducing delay. Thank you for listening.